All right, how did you do? What number did you get in this spot? A 5. How did you figure out that that was 5? So someone says they did 1 plus 4. Okay? And said that was 5. Anybody find a different way to figure out that it was 5? Just keep counting down this row. The pattern is 1, 2, 3, 4, 5. Good. Excellent. Then you got this one as 5 as well. How did you get that second 5? Same way? Did anybody get that second 5 in a different way? I mean, it's still the 1, 2, 3, 4, 5 down this angle. And still 1 plus 4 from above. Did anybody use symmetry? Say, I notice everything on the left side is the same as the stuff on the right side. So since there's a 5 on the left, there must be a 5 on the right. Okay? What we're going to find out is in Pascal's triangle, there are a ton of very cool patterns. We're just looking at a few first ones on how you find 5. So then in the next row, the next box, what did you find? 15. And then by symmetry, this one's 15 as well. How did you get that 15? Okay, again, you could add the 2 above. This is probably the most common way to find something in the next row of Pascal's triangle, adding the 2 numbers above. Did anybody figure that 15 out in a different way? Like these two? Or that, yeah, we've got that already. We've got 5 plus 10 is 15. But we have another way that we could get that 15. Okay. Yes, so sometimes this is called, in Canada, I like to call it the hockey stick identity. Whereas if you make a hockey stick starting from the edge, all the numbers in the shaft of the stick add up to the number in the blade of the stick. So 1 plus 2 plus 3 plus 4 plus 5 equals 15. So I'll move that one, whoops. Move that one away. It works, start from this end. If I make a mini stick, 1 plus 4 plus 10, that equals 15. And that works anywhere. So if I start here and I go along, check, does 1 plus 3 plus 6 plus 10 equal 20? Yes. So that is called the hockey stick identity, or the sock identity if you live in a country that doesn't have hockey sticks. You could call it a sock or a stocking, I'm not sure, whatever you'd like. You could also find the 15 from this row. 1, 3, 6, 10, 15. What pattern do you notice? Goes up by 2, goes up by 3, goes up by 4, goes up by 5. And this row in particular, on their own, are a certain type of numbers. They're called the triangle numbers. Here's your first triangle number, that dot. Can you imagine that it's a triangle? Good. Sometimes the first one doesn't work very well. The second one, though, if I add 2 dots on the bottom, that looks more like a triangle. The third one, the fourth one, can you see the triangle now? You see why maybe they're called the triangle numbers? And how many dots are in the first one? 1. How many dots in the second one? 3. How many dots? 6. Then 10. The next one will have 15. And the triangle number is just what we saw in this hockey stick right there. They just add up your integers, 1 plus 2 plus 3 plus 4. And the next one will have 5 on the bottom, so it'll be 1 plus 2 plus 3 plus 4 plus 5. Okay, write the next row. And if you got the next row already, write the 9th row as right row 9 as well. What does it start with? 1. Why does it start with 1? You could do 1 plus 0. You could use this same idea. Well, there's nothing over there, so 1 plus 0 is 1. Or you could just say, well, they all start with 1. So I think it should start with 1 again. Okay? 1, and then 7, 21, 35, 35, 21, 7, 1. And the next row, 1, 8, 28, 56, 70, 56, 28, 8, 1. So you'll find that the adding idea, where you just add the 2 above to get the next one, works out really nice. Where have we seen this adding idea before? Quite, but in this class, where have we seen the adding? In our factorials, what questions did we have the adding thing up? What kind of question? The street routes, right? When we counted all the street routes from one, as Johnny was trying to get to the library or wherever he was trying to go, and we counted the street routes, this pattern showed up. In fact, this is the same pattern if you've ever played the Plinko game. Have you ever seen the Plinko game where you drop a disc and it goes clink, 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 all the way down? This shows you that if you dropped it there, there are 70 routes that would go to this spot. And it's very unlikely that you'll end in the corner.
So that's why they have all the good stuff.
That's why they have the good stuff in the corners. But this is your number of routes that would get to each of those spots at the bottom. Now, some other fascinating things about Pascal's triangle. If we add up the numbers in each of the rows, 1, 1 plus 1, 2, 1 plus 2 plus 1, 4, 1 plus 3 plus 3 plus 1, 8. What do you notice? They're doubling, and these are powers of 2. Does that work as you keep on going? Yes, it does. That's kind of cool. And if you think about these numbers as just numbers, 1, 11, 121, what's special about these numbers? They are the powers of 11. This is 11 to the 1, 11 squared, 11 cubed. Check this, make sure I'm not lying, 11 to the 4. But now in row 6 we get a problem with the tens. Have you ever wrote a tens number in one digit? No, that doesn't quite work. But it still works if you work from left to right. I have a 1, I have a 5, I have a 10, so that means I have to carry over the 1 to here, which makes 11. I carry the 1 over to there, 6, 1. Check that out on your calculator, and sure enough, that's 11 to the 5. Whew. That's pretty cool. And then, let's see, any other patterns? Oh, I'll show you one more pattern. How many people have heard of the Fibonacci numbers? Fibonacci numbers are 1,
2, 3, 5.
all right, if you know them, don't say the next one. I want you to see if someone who, if this is the first time you're seeing the Fibonacci numbers, the next one's 8. See if you can figure out how to figure out the next one. You can figure out the next one by looking at the previous ones. What's the pattern? What's that? What do you think the next one is? 13. Good. Now you can't answer the next one. Someone else define the next one. 21. Yes. Okay, someone else has to figure out the next one. $34. So how do you find the Fibonacci numbers? Add the last 2 to find the next one. Now these numbers are famous. We could have a whole class just talking about Fibonacci numbers and how they show up all over the place in nature and in music and in architecture and in your everyday life you see the Fibonacci numbers, but we don't have time right now. So right now we're going to see if we can find the Fibonacci numbers in here. So where do the Fibonacci numbers appear? Well, I'm going to draw what seems like a random line and move that off to the side. All right. Now that I've drawn that random line, now can you see the Fibonacci numbers? Oh yeah, obviously, right? Well, if I have that line run through numbers, well, the first one it hits is 1. Next one it hits is 1. But when I hit this one, 1 plus 1 is 2. 3. Depends if my slope is quite right or not, yeah. That one hits 5. The next one hits 8. And you keep on going all the way through, and you keep hitting Fibonacci numbers all the way through. So Pascal's triangle is very cool. It has tons of patterns. In fact, other patterns that you could, if you make a really cool shape with numbers in it and it becomes famous, it might get named after you. Like put numbers in a circle and you've got like the Crockett circle or something like that, and it'll be known forever. But the numbers have to mean something. In this one, they do mean something. They come up in a lot of different ways, and they show up a lot of different patterns, which is just crazy. Like another famous triangle is named after a mathematician called Sierpinski. It's called Sierpinski's triangle. Sierpinski's triangle is also in Pascal's triangle. Sierpinski's triangle, if you just shade in all the even numbers with upside down triangles, and the next ones will be, and so on, you will get Sierpinski's triangle. I'll quickly show you some. So we've already figured out row 9. But now the question is, why are we doing Pascal's triangle in our permutations and combinations unit? Well, here it says, look at 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. Figure those out. I'm going to do it for you. Mental math quickly. What do you notice? These are combinations. And that is, those are 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. That matches up with one of these rows that we can hardly see anymore.
1, 4, 6, 4, 1.
Wonder if I can copy. Paste is gone. That makes me not very happy. Try that one more time. Copy. Paste. There we go. That's one of the rows. Oops, that's not the page I wanted to copy it on either. Man, what a tough day. 1, 4, 6, 4, 1. And what happens if you would do 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, and 5 choose 5? You would get 1, 5, 10, 10, 5, 1. And so also, every single row of Pascal's triangle connects to a combination. So we can now redo Pascal's triangle with combinations. The very first one, 0 choose 0, which is kind of weird to think about. You have 0 items and you don't choose any of them. There's one way to do that, although it's a little hard to imagine. But if we fill this out, this will be 2 choose 0, 2 choose 1, 2 choose 2. And then 3 choose 0, 3 choose 1, 3, choose 2, 3, choose 3. 4, choose 0, 4, choose 1, 4, choose 2, 4, choose 3, and 4, choose 4. So there's a connection to combinations. And now how are we going to use this connection? Because this section is called the binomial theorem. So what does the binomial theorem mean? What does it have to do with? Well, it has to do with binomials. That was nice. And what happens when you take something like a plus b and square it? Well, that's something you already know how to do. What is it equal to?
A squared plus 2ab plus b squared.
A squared plus 2ab plus b squared. Okay. And something that's even easier, I could do a plus b to the 1, which is just a plus b. Are you okay if I put a 1 in front of the a squared and 1 in front of here and 1 in front of there and 1 in front of there? And what would happen if you just did a plus b to the 0? Well, that's equal to 1. Good. What do you think a plus b cubed is equal to? You could do this the long way. You could multiply it all out. You're going to get an a cubed. And what do we notice? Do you think you could do a plus b to the 4? There's more than just one pattern here, right? Because you have to figure out. So let's try. A plus b to the 4 will equal a to the 4. You'd have one of those. 4. Now, what are the variables going to be with this one? A cubed and, no, and b. Plus, and now we have a squared, b squared. Plus, do you notice a pattern with the exponents? Okay. With the first one, you start with a to the 4, and then you went a to the 4, a cubed. You're going down by 1, a squared, a, and then you have no a's. With the other one, you don't start with any of them, but then you go up. 0 here, then 1, then 2, then 3, then 4. So why do our combination numbers show up in the binomial theorem? Well, what's happening when you multiply? So let's start with one that you know. Let's just start with a plus b times a plus b. Because you know that these are all of the choices that you have when you multiply it out. The only way that you can get a squared is with, I'm going to change my arrow colors here. I'm going to change this one to dark. Ooh, that changed both of them. Don't like that. I'm just going to delete. I'm going to just delete them and start again. So I'm going to make the a times the a in green. I'm going to make the a times the b in red, the b times the a in red, and I'm going to make the b times the b in black. Okay? You just watch, okay? Because this is an explanation. So the only way that I can get the two a's, a times, there's only one way to do that. There's two ways of getting an a and a b, an a and a b, hence the 2 number in front. And there's only one way to get both b's. Now, how does that connect to combinations? Well, this number was 2, choose 0. This number is 2, choose 1. And this number is 2, choose 2, according to our Pascal's triangle with combinations. So one of the ways we can think about the 2, choose 0 is, in order to get an a squared, how many b's do I need? I need 0. So in here, I have two places where I could choose b's. I could choose a b here, and I could choose a b here, and I don't want to choose either of them. So I'll go 2, choose 0, and that will choose only a's. In the second one, 2, choose 1, a little bit easier to fathom, is in order to multiply to get an a and a b, I need to choose one b. I either need to multiply including this b, or I need to multiply including this b. I have two b's to choose, and I need to choose one of them to get an a times b. Hence, that number is 2. And same thing with the b squared. There's two b's. I need to choose both of them. There's only one way I can do that. So I'm going to erase these, and now we're going to extend this I'll probably run out of colors, but there would be sort of a similar thing. We never do like multiplying with 4 things very often. But you could have an arrow system for this as well. For example, how do I get a to the 4? The only way to do that is a times a times a. Do I have enough? Yeah. That's the only way I can get a to the 4. Hence, the number in front of a to the 4 is 1. To get an a cubed b, and I'll choose purple for this one. Can you see that I could get an a cubed b with a, that's 1, 2, 3, and then b? I could also get it with a, b, a. I could get it with b, a, and I could get it with this a, b, a, there. And if you did arrows this way, it would get terribly confusing because there'd be so many arrows in the end, and you'd have some kind of acronym that would probably be like and you'd have to remember how many oys were in there in order to do it, and it just would not work, right? Well, it would work, but it would just be not pretty. So what's happening with this one? Well, this is 4, choose 0. This is 4, choose 1. Can you see with my purple arrows, what I was deciding is which b I was going to use to go with the other 3 a's. And since there's 4 b's, I just need to choose one of them, and that gave me 4 pathways to get an a cubed b, hence the 4 in front. It would be even worse if I changed a different color to figure out how many a squared b squareds there's going to be, because I need to choose 2 b's. The order doesn't matter, because if I chose this b and this b to go with this a and this a, the order doesn't matter which way I chose those 2 b's, hence 4, choose 2. And if we counted all the different combinations of choosing 2 b's, we would get 6 of them. And when this is multiplied out, you get 6 a squared b squared. This is the binomial theorem, and we're going to use this to expand things. Because if you would have done this the old way of just multiplying this out, what you would probably have done is you would have multiplied that together, because you know how to do that, and this together, got a squared plus 2ab plus b squared, and then multiplied those two together and gotten something big and combined all your like terms. It would have been a little bit messy and a little bit long. So the binomial theorem helps make it quicker, shorter, and hopefully not a lot shorter, but nicer.